our lesson plan lah. Because I want to show to you. Okay, currently we already cover topic until topic numerical, right? Last class we cover until numerical, right? Ingat tak? So okay, so far we already cover about the process linearity, then open loop test technique, which is tangent method, reformulated tangent method, and then we already cover about time constant, numerical method, and lastly I already cover about the time constant numerical. Last time we calculate the TC using numerical technique based on 2-point method kan. 2-point and also tangent and point method. Ingat lagi tak?
Ingat.
Okay, good. So for this week, I will cover about the optimum controller setting. Actually, optimum controller setting ni quite straightforward lah. Because previously you already learned about RR, how to calculate the RR, TD and TC, right? So for the optimum controller setting, we just make use the value of RR, TD and TC that you calculate before, and then we calculate the value of P, PI and PID. Okay, so we open our notes. This is the last part we cover before midterm break. So this is the numerical technique. So I already teach you on how to calculate RR, TD, and TC. So basically, according to lesson plan, I already cover up to week 8 punya lesson plan lah. For the TC also, I already cover 2-point method and also tangent and point method. Based on the calculation we perform before kan. Semua ni kita dah buat. Sampai sini kita dah buat ke? Calculation of time constant, tangent and point and 2-point method dah kan? I think this one already covered.
Dah.
Because I already show you how to determine the n plus 1. Semua ni dah ada kan? Table ni pun dah buat ni. Okay. So, okay, now we continue on optimum controller setting. Okay, basically, okay, for the optimum controller setting, we will make use the data that you calculate from your response, which is RR, TD, and TC. So we insert this RR, TD, TC into the tuning rule formula. So basically, the tuning rule is a set of formula that used to calculate P, PI, and PID. So basically, we have 8 choices of tuning rule. So you may choose what kind of tuning rule that suitable for your process. So we have a few criteria lah to select the tuning rule. Okay. So the first one The most famous one is a Ziegler-Nichols. So basically this Ziegler-Nichols, we call it as ZN tuning rule. This one is suitable for the QAD response. QAD response, you all tahu tak apa?
Saya tak tahu.
You belajar CPE501 ni? Ke macam tak pernah tahu? Macam tak pernah ingat daripada CPE501 dah ambil kan?
Saya tak ingat ada.
Okay, so QAD ni is a quarter amplitude damping. This is a type of response. Okay, so I just recall back the type of response that we have. The most common one lah. Wait let me open the notes first. Okay. Okay. To recall back, so this is QAD response. The response for the QAD, normally we have a slight oscillation at first. You nampak this part ada a few oscillation, and then this response will reach it set point lah. Tapi it take a longer time lah to reach the set point. So basically, this is QAD. So we have the other type of response, which is oscillatory. Oscillatory shows that the process is unstable. The response is unstable because these fluctuations never ending, and the response didn't reach its set point. So memang the response that we get ni oscillate lah. So the other type of response we have underdamped. Underdamped, that means there is a oscillation at first, and then after that, this one we call it as overshoot lah. To be specific, overshoot lah. Tapi this overshoot basically terjadi disebabkan oscillation lah. The process response to oscillate. So there is one oscillation, and then the response reach its set point. So this one we call it as a underdamped. Overdamped, that means there is no overshoot. The response didn't oscillate, and the response reach its set point in a fast way lah, lagi cepat lah as compared to the QAD and also underdamped. You boleh nampak lah dekat sini dah terus sampai set point. The last type of response is offset. Offset is when the response didn't reach its steady state. Dia macam overdamped. Dia tak ada oscillation, there is no overshoot, but the response didn't reach its set point. So the error from the process variable ni, PV ni dengan set point ni, we call it as a offset. You faham?
Boleh.
Boleh ada.
Okay, so I go back to your book. I nak bagi you faham je type of response, sebab nanti kita akan pilih the tuning rules based on the response type you. Okay, the first one, tuning rule by ZN, is suitable for QAD response. Okay, and also suitable for performance test, which is set point and disturbance variable. That means kalau you perform a set point to your response, set point change, and then you can use this formula. Okay, other than Zn, you also have a Takahashi. Takahashi normally is suitable for the minimum control area. Okay, next we have CHR. You boleh tengoklah nama kat sini. So CHR normally is suitable, CHR for this table lah. 2.13a, this one is suitable for no overshoot and minimum response time. That's mean your response is same like overdam response just now. Overdam tadi ingat tak yang kita punya respon tu tak ada overshoot pun. Kita terus dapat the set point. Maksudnya respond when it increase and it reach the set point. Okay, the next type which is CHR also. This one, the response, it is suitable for the response with 20% overshoot and minimum response time. So this one referring to?
Under them.
Yes, under them lah. This one. Okay, so the next type is ada dua satu point. Okay. For 2.13a, it's suitable for the set point changes. Same goes 2.13b, set point changes. Okay, we have the other type. For the CHR, the tuning rules divided according to set point and also disturbance variable. Same, they have two, which is no overshoot and minimum response time. And 20% overshoot and minimum response time. But the difference is this one, this table 2.13c is suitable for disturbance variable. 2.13d is suitable for same like 2.13b, but this one is for disturbance variable. Okay, the fourth rule, which is Cohen-Kuhn. So for the Cohen-Kuhn, for the QAD response, you may use this table. This one is for disturbance in load variable. So you kena, when you want to do a tuning, you need to, first thing first, you need to identify your response. You tengok dulu response yang you dapat tu macam mana. What kind of response, overdam ke, underdam ke, QAD ke. Then from that one, you tengok pula your case. Sekarang ni you tengah buat performance test apa? Is it set point or is it disturbance variable? So based on that, you can choose your tuning rules. So for Fuji and Yoshikawa, you can use for the minimum control area and suitable for performance test change in set point. Okay, so basically you have 5 lah kan? 1, 2, 3. Ada 5 type of tuning rule. Okay, boleh ke?
Boleh.
Boleh.
Okay, so as you all know, we have 3 mode of controller, which is P, I, and D. And normally we will combine P. Sometimes we will use P only, and combination of PI and combination of PID. Yeah, so basically we have a specific processes that's suitable for each of the controller mode. For example, like P normally suitable for all processes, but sometimes the process may not stable at the set point because maybe the P controller is not good enough to control the process. That's why we will add up some the other controller mode like I and also ID. So for the PI, normally is suitable for flow control system, pressure control system, and liquid level control system. And for the PID, normally is temperature lah. Macam mana kita boleh dapat tahu mode yang mana sesuai dengan proses. So basically is based on the previous response that researcher study lah. Normally the researcher will try to install ataupun integrate each of the controller to their system. Then from the response obtained from P, PI and PID, they come up with the best controller mode for their system. So that's why kalau you ada baca journal ke, normally the journal is about the best PI controller for water tank system. Because the one that study on the controller, normally researcher for the control system, they will focus on the best response for that process, for that particular process. Dia takkan sama tau. That means kalau you pakai temperature dengan level, you tak boleh pakai the same controller. Because each process have their own response. And the response, kalau logically kita fikir pun, the temperature will take a longer time lah to reach the steady state, right? As compared to the flow or liquid, betul tak?
Betul.
So that's why the researcher come up with this kind of table lah, which is which process is suitable with which mode of controller. Okay, nanti you akan guna pakai lah this table and also the tuning rules to choose which tuning rule is suitable for your process. Okay, kita try buat example boleh? Simple je sebenarnya example dia. Sebab you dah tahu dah calculate RR, TD and TC kan? So sekarang ni actually it is a continuation from the tangent method or reformulated tangent method. And also from the 2-point method, tangent and point method. Yang sebelum ni yang you dah belajar TD, TC and RR, how to calculate tu, the continuation is this part lah. Di mana you dah dapat value TD, TC and RR, you just key in inside the formula. You nampak Okay, let's say we take one lah, Zn kan. Previously you calculate RR, TD, right, from the response, betul tak?
Betul.
So from the value of RR, hari tu you calculate and then you stop sampai situ, betul tak?
Betul.
So basically, why you calculate RR, TD and TC? Because you want to solve for the controller mode. That means you nak dapatkan value untuk controller mode you, P, PI and PID. So bila you dah dapat P, PI and PID and you masukkan insert into your process system, and then you start to, that means bila you dah masuk P, PI and PID, you start to tuning your response lah. Mungkin previously your response, previously you dapat your response macam ni. So when you calculate the RR, TD and TC based on the response ni, and then you masukkan the value of RR, TD and TC pakai P, PI, PID. So you start to run back. Maybe your set point ni dekat sini. Your process, maybe lah, I just simulate lah apa akan terjadi. Maybe when you put in P into your process, your response would be like this lah. Mungkin dia akan naik, dia akan mula stabilize lah. Maksudnya dia dah remove all the oscillation inside here. Tapi normally P response will not reach the set point. Normally kita ada a few offset lah dekat sini. Ni kalau pakai P lah, normally lah. Tapi ada certain process, dia dah sufficient. P dah sufficient. Maksudnya dia dah boleh reach set point. This is P. Kalau PI, normally from this QAD ni, maybe dia boleh jadi macam ni. Dia buang the oscillation, but there is a some overshoot. This one we call it as a underdamped kan. So maybe PI like this. Okay, then you install PID. Normally PID is the most robust technique lah. Yang maksudnya the most robust controller lah. Dia akan make sure the offset error is reduced, the overshoot is reduced. Normally, we will get this kind of response using PID. So from these three, which one is the best? P, PI, PID.
PID.
Yes, PID controller lah is the best. So why we do this tuning? Because we want to get the best response. Ni yang paling penting sekali. Sekejap Wait Okay. So now we try to do, you dah faham kan kenapa, apa fungsi kita buat optimum controller setting ni kan? You boleh nampak kan?
Nampak.
Okay, good. Okay, so now we try to do at least 3 tutorial lah. Okay, the first one, it is an open loop test has been performed to a flow control loop. Okay, kat sini kita dah ada 1 point which is flow control loop. Okay, so the process has been analyzed for process characteristic and summarized as in table 2.21. So from your response previously, you dah calculate the TD, TC and RR. Okay, now you need to calculate the optimum controller setting for the flow control in which the process will behave like a QAD type of response when a change in set point is made. Macam I tunjuk tadi lah. Macam ni. Maybe you dapat QAD macam ni lah. So at first bila you buat open loop test, you get this QAD response. So like what I mentioned, why we want to learn about this one? Because we want to get the best response. So from the QAD, we can tune it to get the best response by inserting the controller mode lah, which is P, PI, PID. Okay, so now, okay, we know that this is a QAD type response. Okay, and the other point is there is a change in set point. QAD change in set point. So which table you need to use? Yang mana satu you rasa boleh guna?
2.1.4 Kohen Kun.
2.1.4 Kun. Okay. Other than that?
2.11.
1.11 and also tak ada dah dua ni je kan. So basically between these two lah you boleh pilih. So at first we try to choose this 2.1.1. Dia tak kisah tau, you boleh choose. Kalau you nak calculate using 2.1.1 pun, 2.1.4 pun boleh. Okay, at first we choose table 2.1.1 which is QAD for set point, Ziegler curves. Okay. For the flow, which one is suitable? P, PI or PID?
PI.
Yes, PI. Senang kan? So PI, you go to the ZN table, you see the formula of PI. Which is this one lah, terus you directly ambil yang ni. You ambil ini. PI lah. Okay. So this is the formula lah. PB is proportional band. You input the RR, TD, and for the I, you input the TD. Okay, we try to calculate. So for the PB, this one RR, 0.575. Next is TD, 0.83. Okay, let's calculate together. You dapat berapa?
53.02.
Yes, 53.022, right? Okay.
Betul.
The value of TD is 0.83. Okay. So what is your answer?
2.7639.
2.67. Kita round up sampai 3 decimal place jadi 2.764 lah kan? Okay, after you get this PI, what you gonna do? P dengan I ni. You dah pergi lab kan?
Belum.
Oh, tak buat lagi hands-on daripada dekat lab.
Sekejap lagi.
Oh, kejap lagi. So nanti you just masukkan je lah the value of P dengan I ni. Dekat dalam your setting tu, controller setting tu.
Madam, kiranya yang value yang kita kira ni optimum value lah untuk kita punya proses tu.
Betul.
Oh, okay.
Sebab you at first you dah calculate, you dah dapat your response. Kalau you perasan kat sini dia cakap open loop test has been performed. Maksudnya you dah buat open loop test, you dah come out dengan satu respon. You dah dapat respon yang I tunjuk tadi, which is QAD tu kan. Punya respon yang macam naik and then macam ni kan. Ni lah respon yang you dapat masa you buat open loop test. So from the open loop test, macam kita belajar before this, you calculate the RR, TD and TC based on this respon yang you dapat mula-mula. Open loop test is the respon di mana there is no controller been installed. Maksudnya your pure process response. So bila you dah dapat RR, TD and TC, you calculate the P and I, then you insert into the controller setting, and basically dia dah tune lah this process, dia akan tune lah, the controller akan tune this process using the setting ni menjadi satu lagi proses yang lain. Maksudnya bukan satu proses yang lain, mendapatkan respon yang lebih baik. Daripada proses ini, daripada respon ini, maybe bila you dah guna controller setting tu, your respon tu, dia akan keluar jadi macam ni. Lagi baik kan? Betul tak?
Betul.
So, the change of the response from this to this, kita panggil tuning. Inilah tuning. So, when we do a tuning using the tuning rule tadi yang you pilih tu, we can come up with the controller setting. Setting tu adalah P punya value, I punya value, D punya value. That value tu lah yang you set dalam your controller. That's why kita panggil optimum controller setting. Boleh?
Boleh.
Okay, tapi sometimes, okay, I bagi satu situation lain lah. You dah masuk tuning setting ni kan, controller setting yang baru. Mungkin you tak dapat macam ni. You dapat macam ni tapi ada sikit macam tu dan macam tak berapa nice kan dia punya respon ni. Betul tak?
Betul, madam.
So maybe you can further tune. Kita panggil fine tuning. Macam you buka radio lah. You tune dapat satu channel. But the channel tu dia macam sama-sama. Dia dengar, tak dengar sikit. And then you tune sikit lagi and then you dapat jelas, dengar yang jelas. Itulah sebenarnya you tune. You buat tune, first tune and then fine tuning lagi untuk dapat betul-betul yang jelas. Boleh faham?
Fine tuning tu guna method yang sama juga kan, madam?
Fine tuning tu dia basically dia ada lagi method yang lain which is you boleh buat fine tuning tu. Tapi normally kita akan guna up to this tuning rules je lah. Dia ada lagi tau. Actually dia ada lagi advanced tuning. You boleh pakai dia ada rules ataupun you boleh add up dia ada what we call like macam bukan adjuster lah, kita add up, kita guna pakai method atau calculation yang lain lagi untuk dapatkan, untuk fine tuning lagi. Daripada value yang you dah ada ni, kita tune lagi this value. Like IMC pun, tapi normally IMC tu at degree level kita tak perkenalkan lah. IMC tu normally up to during master and above lah. Normally researcher lah, dia nak study in detail lagi for that process kalau dia nak buat fine tuning. Macam tu lah.
Maksudnya untuk fine tuning value untuk RR dan TD tu masih value yang sama lah.
Betul. RRTDTC masih yang sama. Yang tu yang memang sebab kita dah, yang tu memang purely ambil daripada your first respon yang asal. Yang kita tak usik apa-apa pun. RRTDTC masih yang sama. Kita ada lagi tuning on closed loop pula. Sekarang ni you buat tuning on open loop kan. Maksudnya you dapat yang you dapatkan RRTDTC daripada pure respon yang you tak install controller pun lagi. Actually kita ada satu teknik di mana controller dah di-install. Macam sekarang ni bila you masuk dah controller, tiba-tiba you rasa macam tak okay. And then you boleh buat tuning based on the maksudnya closed loop system. Maksudnya proses yang dah ada controller, you buat lagi fine tuning dekat situ. Macam itulah dia punya konsep. Normally sistem yang sangat orang cakap fluctuate lah, non-linear. No. Kalau sistem-sistem yang sedia ada ni normally kita dah ada cara dia, means kita dah boleh guna pakai teknik-teknik yang sedia ada lah. Untuk sistem-sistem yang baru lah, researcher akan study and at first approach memang dia akan guna open loop test and then dia buat tuning, cari tuning setting. Kalau tak boleh dia akan further lah, buat closed loop test pula ke, daripada closed loop test buat lagi fine tuning. Boleh faham?
Faham.
Okay, good. So kita proceed tutorial 2. Kita habiskan sampai tutorial 3 lah. Okay, so tutorial 2 is about open loop test. It's about the temperature control loop. So an open loop test has been performed. So we already get the process characteristic, which is TD, TC, and RR in this table. Okay, so you need to calculate the optimum controller setting for temperature control loop, in which the process will behave like an algorithm type of response when a change in set point is made. Okay, so algorithm tadi, which one?
2.13a.
2.13a. Okay, yes. For the overdamp, kita tak ada overshoot, betul tak? Macam saya tunjuk tadi kan? So we will use CHR for the change in set point. Okay. So kat sini dah tulis overdamp. So change in set point, kita pakai CHR. Okay, looking back the table, normally temperature control, PID is most suitable lah. Okay. So directly use the table. Inilah kita ambil yang bawah inilah. 167 RRTD, TD and 0.5 TD 4D. Okay, RR kita tadi berapa? 0.00365. So TD 28.8. Can you calculate for me? Berapa?
17.555.
17. Semua dapat yang sama ke?
Sama.
Okay. Okay, I directly take the value of TD lah, which is 28.8. D is 0.5 times TD, which is 28.8. Okay. Can you calculate for me?
Dapat 14.4.
14.4. Okay, moving on. Tutorial 3. Okay tak tutorial 2?
Okay.
Okay. So tutorial 3 is about pressure control loop. So we have RR, TD, and TC in this table. Okay, you need to calculate the optimum controller setting for the pressure control based on Cohen-Kuhn tuning rule. Cohen-Kuhn tadi ada satu je kan? Betul tak? Yang ni je.
Betul, madam.
Okay, good. So 2.14. Okay, 2.14. So you boleh tulis kat sini lah. Kohin kun lah. CC. So mode of controller is pressure, right? Pressure we use?
PI.
Yes, PI. Okay, so this is the formula for P and I. For Kohin kun, okay, kita ada mu kat sini ni. Mu ni stand for apa? Apa formula dia?
TD over TC.
Yes, TD over TC. Okay, so now we calculate the mu first. TD over TC, which is 2.86 divided by 22.3.
Dapat 0.128.
0.128 Semua dapat yang sama ke? I pun dapat yang sama. So next we move to P. So for P, RR is 0.105. TD is 2.86. Mu is 0.128. Okay, can you calculate for me the value of PB?
Dapat 29.685.
29.685. Semua dapat yang sama ke?
Dapat.
Okay. Okay, yang ini pula untuk I. TD is 2.86. Okay, dapat berapa?
7.518.
7.518. Semua dapat yang sama ke? Dapat yang sama ke?
Dapat sama.
Sama, okay, good. Okay, so ada soalan tak untuk tutorial 3?
So far so good.
So far so good Nak move ke tutorial 4 ke atau you nak stop dah?
Boleh je kot. Nak teruskan. Saya
Okay.
tak kisah mana-mana.
Okay, kita cepat sikit lah untuk ni. Sebab you pun ada lab kan kejap lagi. Okay, so tutorial 4 yang last which is flow control loop. Okay. Okay, we need to calculate the optimum controller setting for the flow control in which the process will behave like a QAD type of response when a change in set point is made. So tadi QAD you ada dua step kan yang you boleh pilih, dua tuning rule kan yang you boleh pilih kan? 211 dengan 214, betul tak?
Betul.
So sekarang mungkin you boleh pilih 214 QAD set point. Oh, sorry, Kohin kun is for disturbance in load variable. Jadinya you tak boleh pilih yang ni lah sebab bukan set point. That's mean ada satu je lah. That end je lah you boleh pilih. Okay. Sebab Zn for the set point. Kohin kun for load disturbance. Okay, select the mode. Mode dia apa? Flow control?
PI.
PI. Okay, so calculate. Pakai formula ini. 111.1 RRTD and 3.33. So PB is equal to 111.1 RRTD. So I is equal to 3.3 TD. Try to calculate for PB, calculate for I. Oh sorry, this is 3.33 bukan 33. Dapat berapa PB?
$74.326.
74.326 Oh yes. 74.326 cent. So for TD 3.33 lah kan? Betul tak?
Betul.
Okay. Okay, so finish on fourth tutorial. So ada soalan tak? Don't forget the ni the units. Oh, patutnya I tulis kat sini. Okay, semua boleh faham
Boleh.
Okay, good. So, kalau tak ada soalan, I think we can stop until here. So, we end our class with Tasbih, Farah and Surah Wal-As.